Ok, bonjour, merci d'être venu. Welcome. So, what we have seen last time, excuse me, we've computed the response of the current in A direction to some vector potential in the B direction, but we wrote it in a gauge invariant way so that we could write the electric field here. And the scalar potential was also contained. And other important thing we said is this F sum rule that we said not last time, but the time before. That's a consequence just of canonical commutation relations. So today we are going to discuss to finish these general properties and start to talk about Green's function towards the end of the class. But before I want to make use of all this formalism to show you one very interesting result, which is that a superconductor expels magnetic field, and you can compute the distance over which it expels the magnetic field using optical conductivity. And optical conductivity obeys some rules. So this is what we are going to discuss. So at zero temperature for a pure material, there's a very sharp distinction between what is a metal, what is an insulator, and what is a superconductor. And this is what we are going to discuss. And something called the Drude weight. Okay, so any questions regarding last time or? Okay. So, il y a Pierre-Antoine qui est là. Bonjour, Pierre-Antoine.
Salut.
So, let's start with this. Let me, you see here is the current correlation function that comes in. So here, let me rewrite this sum rule in terms of current correlation function. So what we can do here is recall current conservation. So current conservation can be written as omega times rho of Q and omega is equal to Q times J, okay? And it's a scalar product, so it has to be longitudinal. In other words, the dependence on position has to be in the same direction as the current. So let me just divide by Q square here. And then you see that I can use omega rho is equal to Qj. And so if I divide by omega prime here and square here, so I have done nothing, except that now omega square rho, this is rho of omega, rho of minus omega, but we have rho of q, rho of minus q, so this works out. So this omega square times rho divided by q squared, that gives me a current, okay? And it's a longitudinal current, so it's the current in the direction of the in the direction of the spatial variation. So I remove this, and now I have an F sum rule for the current correlation function. Just to make sure that we remember that it is longitudinal, let me choose a direction X for the variation. And so here it will be the current along the X direction and the current along the X direction. Okay, is that okay? So you see that this sum rule is useful, for example, in this case, right? Because we have to remind ourselves that this guy JJ is equal to integral d omega prime over pi of chi double prime j of q omega prime divided by omega prime minus omega plus I eta. Okay, that's the retarded response for currents along A and B direction. So suppose that I have a vector potential A that is a function only of Qx, and it's at zero frequency, okay, and it's in the x direction. I should not have any electrical current coming from this. Why is that?
Well, it's going to be a continuous in time, so it should be a DC current, but there's no reason for it to be there.
Yes, I mean, you see, I remind you that the electric field is minus dA dt minus grad phi. So if there's no frequency dependence, it means that it's time independent. If it's time independent, A cannot lead to an electric field. Okay, and I take phi equals 0. And it cannot lead to a magnetic field also, because the magnetic field is to be, the response is supposed to be transverse. Remember, because the magnetic field is Q cross A. So Q has to be perpendicular, and here I take them in the same direction. So that field is a pure gauge field. And so just a pure gauge transformation should not lead to a real observable current. So if I take J in the x direction, Q in the x direction, and this is at omega equals 0. So omega equals 0. You see that it will work out because these two terms will cancel. Okay, so the F sum rule guarantees gauge invariance. So if I call this quantity D, if I call this quantity D at of Q yes, of Qx 0. So that's so this this is Q0. Then I will look at the metal, insulator, and the superconductor. So I'll make a little table here. So whatever if it's metal, insulator, or superconductor, it should be 0 by gauge invariance. Okay. Now let's look at what is a metal. So as I said, at 0 temperature, there should be a sharp distinction between metal and insulator. So let's take just the free particles. Okay. Free particles should behave like you should behave like a metal. So if I look at the dj dt, it's equal to ne dv dt, which is equal to e square n e over m. Okay. I just use Newton's equation. Now, if I go to Fourier space, it gives me, this here is minus I omega plus I eta times j of omega. So this is q equals 0. It's just take a uniform response. And that's equal to e square n e of omega divided by m. Which means that j is equal to 1 over minus I omega plus I eta times e square n e over m. So what is the conductivity? What leads to dissipation? J is sigma E. And this is the dissipation is the real part of sigma. So what is the real part here of this response? So real part of sigma is equal to, I use the Szukatsky-Weierstrass formula here to write this as a delta function. So I get 1 over minus I times, so this becomes also a minus I times delta of omega times n e square over m, which means that a metal should have a delta function response. Okay. Now, if again we take a if we take some, even if the system is interacting, if it is a metal, it should have a delta function response at 0 temperature with no impurities. Okay. So again, to make the distinction sharp, we need to be in these limiting cases. So now you see that if I do just the same as here, so I look at the response of J in the x direction and J in the x direction. And Q in the x direction. So the two are in the same direction here, so that contributes. And that's in the x direction and Qx. But now I want to look at the, I know that if I take the 0 frequency limit, I will get no response if I have a finite Q because of gauge invariance. So on the other end, if I take the Q goes to 0 limit first, so I take Q equals 0. Zero. Zero. Then you see that you see that I will get a delta function response here like this. So I get 1 over I omega. Okay, so there is a real, then it means that there's a Drude weight, which comes from this. The two cancel. So I get a delta function if I take real part here. So I get that, I get this term with this will give me a contribution to the real part of the conductivity, sigma prime, which is minus pi delta of omega times the real part of chi gx at 0 wave vector and finite frequency minus n e square over m. So that thing is the Drude weight. So sigma prime, I mean real part of conductivity. So you see that the real part here, as you remember using Kramer's Koenig, is the principal part of this quantity. So this is chi retarded, Gg of Q and omega equals this. So the real part here is the principal part of this this quantity. So the principal part of this quantity, as omega goes to 0, is not equal to this. There's a delta function response in a metal. So here I can write that d at the q equals 0 and omega is different from 0 for a metal, and it will be different from 0 for a superconductor, right? Because again, superconductor by definition will transport electricity without resistance. Now, what happens in the insulator? In the insulator, why does this vanish? In the insulator, it vanishes because you see chi r, which is given by this. In the insulator, chi double prime is 0. There's a gap. So chi double prime Gg is 0 as omega goes to 0. And what does it mean? Then it means that I don't need this principal part to do the integral. So as omega goes to 0 in an insulator, I can just remove this because I don't need to worry about the principal part. And then I can use the F sum rule that is here. So it's give n square, n square. So you see in an insulator, it's as if I can interchange the Q and the omega goes to 0 limit. I could not do this in the metal, but in the insulator I can. Okay, so it means that here this quantity is equal to 0. in insulator. Now we have one last thing to look at is the this I will call the longitudinal Drude weight, and then there's the transverse. Do you still see? Oh yeah.
You're going out of frame, right?
I'm going out soon. Huh? I see it
Yeah.
on the screen here, but I think I have a little space. So this will be the transverse. I will define it in a moment. So the result will be that this is a 0, 0, and different from 0 in the superconductor. So what am I talking about? In a superconductor, what happens is that we have that the current J in the y direction varying along the x direction at the zero frequency. So it's a thermodynamic quantity. So we look at zero frequency. J of q y qx is equal to ns e squared over m with a minus sign times the vector potential in the y direction at the qx 0. Okay, I'll show you why that should be the answer. So note that this is the current in the y direction for a variation in the x direction. Okay. So then it means that if I do a gauge transformation, it changes just the longitudinal part of the vector potential. Okay. So this is gauge invariant. So I'm allowed to write this because these two things are perpendicular. Okay, now I know that what will happen, let me tell you in advance what happens in the superconductor. So if I have a superconductor here, and I'm coming with and I have some magnetic field, then in the superconductor, it will penetrate just for a small distance that's called lambda. It will decay exponentially with a length that's called lambda. It's called the London penetration depth. So you see, you have the field in the y direction, and in the x direction it varies. So that's the transverse response. So let's see what happens here. We have that the curl of B is equal to mu 0 times J. Okay, so there's no time dependence. That's Maxwell's equation. So let's take the curl of this. So let's go back to real coordinates. So I got vary along the x direction. So the curl of the curl of B is equal to the gradient. That's a vector, so there's a gradient of divergence, which is 0, minus the Laplacian of B. So the Laplacian is a scalar and B is a vector. So we have vector equals vector. So if we write this here, we have if we multiply by mu 0 is the permittivity of the vacuum. So if I multiply by mu zero and I take the curl of that equation, you see that I will get minus, so I'll get minus grad square, so it's varying along the x direction. So it's a d square dx square, and b is in the y direction. So by is equal to minus ns e square mu zero. I multiply by mu zero on both sides, and the curl of A is equal to the magnetic field. So by. So the solution square over m. So the solution of this is that by is equal to b0 at the boundary times e to the minus x over lambda. The minus sign cancel here. Minus x over lambda, where 1 over lambda square is equal to ns e square mu 0 over n.
So where is the difference with the metal? Because I don't see where the difference is.
Yes, the difference is that here we have taken the omega goes to 0 limit first. In a metal, if we take the omega equals 0 limit first, and we look in the transverse direction, in a metal, when you take Q goes to 0, whether it's in the X or the Y direction is the same. The metal does not make a difference. Q equals 0 is uniform. So that you see, if I have taken omega goes to 0 first, like I do here, and then I take Q goes to 0, then I have the F sum rule that kills me. I get 0. But so in a metal, I need to take Q equals 0 first, and then omega goes to 0. In the superconductor, I take omega equals 0 first, and then Q, I have to be careful because I need to satisfy the perpendicular constraint. So let's work out what this tells me for superconductor. So for superconductor, I look at the response in the y direction. For variation along the x direction, so I take Qx at 0 frequency, so it's a thermodynamic quantity. So here I have to put Gy, y, and I have to put the Qx at 0 frequency. And here now, this combination is the vector potential. So I have to look at the vector potential. I was writing for an electric field, but in the general result was written for the vector potential. So for the vector potential, I have A in the y direction for a wave variation in the x direction and 0 frequency. Okay, so it means that I have shown now that so this quantity here should be equal to this. You see, I don't have the full sum rule. The ns that I put here was not n in general. So this quantity, if you want, if this is 0 completely, then Ns is equal to N. And in a superconductor, this will not vanish because J becomes a thermodynamic quantity. And in addition, there's long-range order. We have not discussed that yet, but I will discuss long-range order in the momentum. But you can think of J as being okay. Now, here is what I want to show. I will show you the plot and then I will make the proof. So let me share my screen. So you see this? You see a plot here?
Yeah.
Okay. So this is the real part of the conductivity measured by infrared as a function of, as a function of frequency expressed in wave numbers, okay? So this is the, you see my mouse, so this is the conductivity here at high temperature. And you see there's, I mean, the delta function now that I should see in a metal is spread out because of temperature and so on. That's the Drude way. No, so this is measured in a nick-tied superconductor, but I mean, the precise material is not so important for what I want to see. So here, 45K is the green line, okay? So at 45K, we have a conductivity that decreases. And then in the superconducting state, at 27K, you get the red line here, and 10K, you get the black line. So in this here, there is the green line at 45K, that's above the transition temperature. And 10K is pretty close to zero temperature. It won't vary very much after that. So you see there's what they call a missing area here. So I will show you that this missing area that's measured in optical conductivity is precisely this London penetration depth that we just saw. It's amazing, no? Quite surprising. Well, I find it amazing. So let's see how that comes out.